is going to be discuss the linear bound automata under the model of context free and non-context free languages, that is a model 4 of 18 CS 54. After discussing the topics, the Turing machine, construction of the Turing machine, design of the Turing machine, and the some of the problems, we have seen that. Continuation of this, the linear bound automata presentations, the milestones are as follows. We will going to be briefly understand the linear bounded automata for automation of the fixed length. There are challenges are going to be reason that the arises here, so that also we will going to be see in that while designing the model of the linear bound automata. The model also we're going to be observed, that is there is also operations we can perform with help of the linear bound automata. So the operations we can perform with the linear bound automata. So we can see that there is a relation between the linear bound automata and sensitive languages, that is a context sensitive languages. So kind of relation will be there, and there is also the equivalence to this sensitive grammar, the LBA equivalent to sensitive grammar also we are going to be observed, that is. See, the linear bound automata, so that has the length of its step limited to the length of the input string is called linear bound automata. We have seen that Turing machine which have the infinite length and the each that length, the tape will be split into cells. The each cell going to be accommodate the character. So there is a read write control head will be there, that finite control pointing to the particular character. So that is going to be for every operation, that is the input consuming and producing the output, that is a new state due to the movement of the read write head. We have observed that. So that happen for the very lengthy tape. Sometime it is almost beyond the finite, that the infinite going to be there. So that going to be limited to the certain length. So then it become a terminology comes linear bound automata. So length will be linear function will be going to be exercised. So that is going to be considered here, that is. So the is have several tuples. So those 7 tuples we can observe, that is. So Q is the set of what is called the finite states going to be participate in that diagram. So that we have seen that we can solve this problem through the state transition table or state diagram or instantiation description. So thus 3 methods we have seen in the previous discussion. So all those methods also can extend here, designing the non-determinate to that non-determinate parameter, that is Q comma S comma G. D is a direction and Q naught is the initial state, accept and reject. So accept that there are 2 extra tape symbols are included, that is the end markers. So end markers, so left end marker and right end marker, so which are not elements of the grammar. So these are not elements of the grammar. So these are extra symbols are going to be added here. So that we can call as a left end marker and right end marker with a symbol that is a less than symbol or greater than symbol. So these 2 extra symbols are going to be added. The Turing machine begins in the configuration. So that is a Q naught, so less than that is a X and greater than. So less than end marker and right left end marker with its the tape head scanning the symbol left in the cell 0, left in the cell 0. So the right, that is a greater than symbol is in the cell immediately to the right of the input string X, So this is a left and this is a right end marker. In between the left and right end marker, that is a string will be there. So head will be going to be pointing, that is. So these 2 extra symbols are going to be added in this linear bound automata to differentiate with this deterministic or non-deterministic Turing automata. So we can further consider that the discussion, the Turing machine cannot replace the less than or greater than with anything else. So these are the most important one, which going to be enclosed, which going to be have, that is with anything else, nor move the tape head left or right, that is right. So that was a Turing machine. We observed infinite length. There is no end to end. The length end at the either left side or right side. So here that barcode is restricted to make it discretized, to make it is a finite. So that end marker we kept, that is with help of the less than symbol or greater than symbol, that is. So this is a linear bounded automata. Coming out from the Turing machine model. So the Turing machine model was very generic. So that to non-deterministic Turing machine was slightly stripped to certain conditions. So further impose some conditions. So that making a infinite length to finite length. So that we can call as a linear bounded automata. It is a multi-track non-deterministic Turing machine, right, with the tapes some bounded finite length. So that's all. This also the alternative name, the multi-track non-deterministic Turing machine, multi-track non-deterministic Turing machine with the tape some bounded in the finite length, that is. So length of the we can decide that function. So length of the initial input string, that is a constant c. So input strings and constant c going to will be considered. So length will be mathematically we can show that with a certain function, that is a linear function. So the length of the initial tape input strings, that is a constant c, that is going to be considered, that is. So here memory information is a lesser than or equal to c into input for information. So the memory information, that the memory space going to be occupy how many, the input information into constant. So this going to be come out with some numbers. So this number should be the less than that memory information. So that memory information going to be have to accommodate this information, that input information along with the constant. The computation is restricted to constant bounded area. This computation is restricted to the constant bounded area. So that bounding will be fixed here with the constant, right? So that bounding will be fixed with the constant. So that total bounding will be the in between happen that left end marker and right end marker. So input alphabet contains these two special symbols which serves, that we have seen in the previous slide, which serves as the left end marker and right end marker. So these are the two special symbols going to be added for the non-deterministic Turing machine. That is one adjective, that is a multi-track, and other adjectives going to be considered two end markers to limit the length on either side of the tape. So here we can see from this diagram we can able to see. So there are n number of cells are there. So on either side there is a end will be there, tape end. So in the previous the discussion that there is no end at all. So here the leftmost one is a left end marker. So rightmost one is a right end marker. So from this diagram it is crystal clear of this linear bounded automata dimension can be exaggerate or elaborate with help of these two special symbols going to be add, right? So into this the linear bounded automata description to demonstrate this through the tape, that having multi-track non-deterministic finite automata, which means that transitions neither move to the left of the left end marker the transition will be limit. Transition will be cannot go beyond the left of the end marker, left end marker. That is a barcode kept. So earlier it was a it go beyond that. So now that is the barcode is fixed here. It cannot go beyond the left marker nor the right marker, nor the right hand marker. So the read and write head will be enclosed with this within this sandwiched with this left hand marker and right hand marker. It will play only between these cells. The between the this right and left hand marker, how many cells are going to be accommodated? So only those cells going to be observed that some characters will be existing that that is a tape, that is. So that kind of things will be going to be formed here. So that left hand marker and right hand marker are the quite essential component have been introduced here to discriminate this linear bound automata with a non-deterministic Turing machine, right? So though it is also multi-track and linear bound also, the bounding will be fixed by this linear function. So that is a C to there one estimation, that is a C into input information. So that is a boundary condition. So that is the highest one. So the memory information should be located less than this, less than or equal to sin. This, in other words, the end right hand read marker, right hand right head it cannot go beyond the left hand marker. On other side, not go beyond the right hand marker. So this could be this bounding will be fixed by this C into input information, right? So C is a constant. So from this, I hope it is a very clear the concepts we are going to follow, that is. So what we can say that the linear bound automata, that context sensitive and undecidable. So how there is a relation? So linear bound, context sensitive and undecidability. So we have discussed enough about decidability and undecidability. So coming to that, the problem is solvable. Problem is solvable and it is going to be acceptable. The problem is solvable and going to be acceptable, or the solution is going to be acceptable for the particular problem, then we can say decidable, right? So if not, it is not solvable. It is not solvable and there is not acceptable. So that is some contradiction will be there. So unsolvable is a undecidable, right? Unsolvable is undecidable. So that concept we have discussed. So now coming to, we have also discussed just now that linear bound automata. So it is nothing but a deterministic Turing machine which have finite length of the tape. That is going to be barcode or can be fixed by with help of the end mark, left and right end markers. So coming to this context sensitive languages, so that deterministic linear bound automation is always a context sensitive, right? So it is the deterministic linear bound automata having fixing that certain length, so that can also follow the principle of context sensitive languages, right? So coming to this undecidable, so linear bounded automation with the empty language is undecidable, right? So linear bounded automation with some certain strings going to be performed, so that is going to be context sensitive. If no string, that is a empty language is a string is empty, right, is undecidable, right? So this linear bound automata, in other words, it is made for linearity function. It behaves in the linear fashion. So if you are imposing some empty strings to such a the homemade or the situation arises, when a situation arises for such they are created for which we are putting some empty string, then this is a unsolvable problem. So unsolvable become undecidable, right? Undecidable, we have seen that halting problem. So it is neither accept nor reject. So it will be a halting problem. So it will be catastrophe. so it will be stuck in between. So it will consuming the memory space and also the computation space. The that computational aspects will become very costlier for the most of the undecidable problems. So that why the empty language is going to be of part of the linear bounded automata is going to be undecidable. So I hope this the relation between this context sensitive undecidability and linear bound automata, like that tri-corner problem, that is a tri relationship between among these. So understood this the linear bound automata, there are some challenges are going to be faced by most of the scientists. So there are some problems, challenges going to be observed. That is, the first problem is, the first challenge is the class of language accepted by the linear bound automata. The certain languages going to be accepted by certain languages are accepted by linear bound automata is equal to the class of language accepted by the deterministic linear bound automata, right? So it is almost equal to linear bound automata, deterministic linear bound automata. So this problem can be exaggerated succinctly in the language of computational complexity theory. Computational complexity theory. So computational complexity theory is nothing but analysis of an algorithm. The analysis of algorithm are going to be decided, that is the two major aspects. One is called space aspect and other is a time aspects, the memory space and CPU time. So these two are the major component going to be remarkable glimpses in the computational complexity theory. So those aspects always, that too going to be discussed with related to the primary memory or main memory. So the certain protocols or data structures are going to be store some data in the memory. So in that computational complexity, so as we discuss many times, so that that can go to be assess either prior analysis and post analysis. So most of the algorithms design, they will tell in terms of the big O notations and so on, that is prior analysis. The most of the time, sometimes especially in the online or real time applications, so they are going to be execute the program that maybe a computational aspect that related to the profiling of an algorithm. That one instruction, maybe one unit, maybe assignment, maybe comparison, maybe divide, maybe memory load and store instruction. So that going to be consumes more memory cycles. So in other words, it is a huge amount of resource they are going to be used. So that kind of all those aspects coming in the computational complexity theory. So with relate to that theory, so that LBA as emulating some challenges. The first challenge, that is the n space order of n, that is a big O, that is the worst case time complexity. So that big O of n, that n is a linear, n is a big O of n. So that is a non-deterministic LBA. So non-deterministic linear bound automata of big O of n is equal to deterministic space. So deterministic LBA of or big O of n, right? So is the non-deterministic space is equal to deterministic space? So this is the problem. So this is a challenge most of the scientific community going to be notice that. So non-deterministic space of big O of n is equal to deterministic space of big O of n. So that is going to be one problem or challenge. Second problem is whether the class of language accepted by LBA is a close under complement. So for example, the language L1 is accepted by the LBA. If you complement the L1, then we will get an L2. Consider L2 is equal to complement of L1. Is it also going to be accept? So that is whether class of language accepted by the LBA is closed under the complement. So that is a second problem, second challenge. So that is a, is it the non-deterministic space of space going to be consumed of this algorithm, that is a big O of n is equal to CO, that is a co-n space of n, con space of n, that is also big O, co n space of big O of n, that is a O is missing here, sorry for that. So here the non-deterministic linear bounded automata space is equal to counter non-deterministic space, counter, that is CO is a counter, additional one will be there due to this complement and all those, this complement operation. So that additional will be there, that counter non-deterministic space of big O of n, right? So this is a second challenge, second problem they are facing, that is due to the concept of this linear bound automata. So as observed already, the one of the scientists, that Kuroda, a negative answer to second LBA. So there is a negative answers to second LBA problem would imply a negative answer to the first problem. So negative answer is the for second problem, that is also it also would imply implications will be generate the first problem also negative problem, negative answer. So if you get a negative answer for second, and that is also true for the first problem or the first challenge. So there is a negative answer for the second the problem, that is also the first negative first problem negative answer. So that we can say that interdependency will be there. So between this non-deterministic space and deterministic space. So that too, when you are going to be exercise some the complement operation under which whether it is not accepted by the LB or not, so that is going to be tell by the second problem. So these are the challenges are facing from the most community of this theoretical computer philosophy or classical computer theory. But the second linear bound problem has an affirmative answer, is an affirmative answer, which implies that authors proved 20 years after the problem was raised. So it took about 20 years to solve this. So after 20 years the second problem has affirmative answer obtained from the most of the community of the researchers. So I hope this is added to some the dimension to understand the concept of linear bound automata concept. As of today, the first linear bound problem still remains open, that is a non-deterministic space of the big O of n is equal to deterministic space of the big O of n of the LVA linear bound, that's still open. Provide an insight that non-deterministic space of big O of n is a subset of the deterministic space of the big O of n square. So n square, this is a linear, and now it become a quadratic, that is a second order equation. So n square is a second order, it is a quadratic behavior. So this will go to be a big space. So deterministic space will be big space. So whereas a non-deterministic will become the subset of that. So subset of that too, proper set of that deterministic LVA space going to be consumed, that is, but the first one is will be still open. So from this discussion we have understood the what are the challenges are facing, especially the people who are involved some kind of research in these activities. Ultimately that is going to be evolved as a material for studying the further the concept called classical computers, theoretical computers, or automation theory, so on, that is. So that is going to be heap further to study in depth, that is. So going to further, that is we have used the notations as we said, that is a n space, that is a non-deterministic Turing machine, and D, that is a deterministic Turing machine. So that is a deterministic Turing machine. So that going to be the say about this LBA regarding. So that CO is a counterpart of that LBA, that is. So model of the LBA, the model of the LBA, we can have that the n cells, and we have said that end markers, that is the input tape, and read head moving to the right only, that is. So here we can going to be discuss that is a parent control, that read write head will be there. So then we have a the memory, that is a working tape. So working tape will be evolved here. So that working tape will be pointing, that is a kn cells. Kn cells will be there, right? N cells for the main tape, and the read write or reading move to the right only. So here the working tape will be there. So that is a kn cells, not to strip down the infinite length. Let us consider the input strings W with that nth length of the W is equal to n minus 2. Input strings W can be recognized by linear bound automata. If it can also be recognized by Turing machine using a no more than kn cells, the maximum is a kn cells of input, right? So maximum is a kn cells will be essential that. So where k is a constant specified in the description of the LBA. So in the earlier slide I maybe used that c is a constant. So now is a k is a constant. More or same, that that say c, here k. So description of the LBA. So the value of k does not depend on the input string, but it's purely property of the machine, right? So that string going to be multiplied, that is a kn, that is properly that machine, that is. Whenever we process any strings in LBA, we shall assume that the input string is enclosed with the end markers C and $. So that is the left end marker and right end marker. So these two additional juvelry as added to deterministic Turing machine, it become a linear bound automata that we discussed in the previous slides. So coming to that, so what we can say about a model of linear bound automata. Model of linear bound automata can be represented by the block diagram. So block diagram we have seen in that. So there are two tapes, one called input and other working tape. Two tapes are there, one for welcoming the input, the other one will be make some workspace, kind of workspace, or some temporary, there is some intermediate results are going to be evolved in between due to the continuous computations. So that going to be there in certain time. On the input tape, the head never prints the and never moves to the left. So that will always go towards the right side, from left to right. So that is a fix. It not displays that particular, but it moves towards the never moves to the right side. On the working tape, the head can modify the contents in any way, that is without any restrictions. So that restrictions are there for what is called the input tape, and no restrictions. The restrictions are relaxed for working tape. So working tape is like workspace, as I said. So we can use there no bounding restrictions. The any barcodes are there, that is have freedom to write some information, read some information in the working tape head. In the case of LBA, an instantaneous description denoted by that is a q comma w comma k, right? That is the ID is what? Instantaneous description. What is that ID? That is a one of the method to provide a Turing machine problem solution. Here we can say one of the way we can provide a linear bounded automata solution. So that can be denoted by q comma w comma k, that q comma w comma k, that is where q belongs to small q belongs to big Q, that is the finite number of states which could participate in the, that is a first tuple, which is most of the time we discuss from the, even from the deterministic finite automata concepts what we discuss so far. So W belongs to that tape symbol. So W belongs to tape symbol, that is the lambda, and K is the some integer between 1 and n. So that is going to be the major dimension for linear bound automata. The transition of the ID is a similar, except the K changes to K minus 1. That is changes. If the read write head moves towards the left and K plus 1, if the head moves to the right. So read write head moves to the left and right. So to that to K plus 1. If the head moves to the right, K plus 1 towards the right side. The language accepted by the LBA is defined as the set that is belongs to W belongs to the sigma sigma and the concepts are going to be discussed here. So that is defined as a set of this one. So continuous of this operation, we can see that. So we can observe some operations of this linear bound automata. So that non-deterministic Turing machine, LV is a non-deterministic Turing machine that satisfies the three conditions. What is a condition? Input alphabet includes two special symbols serving as a left and right end markers, we have seen in the previous slide. So transition may not print other symbols over the end markers. So there is no displaying the red character, the character which you read by the read write head. So that because the end marker are enclosed there. So if its transition may neither move to the left of the leftmost end marker nor right of the right end marker, that will not go beyond. In other words, instead of having potentially infinite tape on which to compute, so infinite tape will be prevented here. So for which computation is restricted to portion of the tape containing the input plus two tape squares holding the end markers. So the input plus the two tape symbols will be, end markers will be there. So an alternative will be going to be, say that less restrictive definition. With help of this less restrictive, that privileges will be encouraged. So it possesses a tape made up of cells which comprises characters from the finite alphabet. So it possesses the cells that will be emphasize the symbols from finite alphabet. A head can read from or write to one cell on the tape. One cell on the tape at a time can move and finite number of states. So this is was even there in a Turing machine, but there was infinite. So here we have finite number of states. So an LBA differs from Turing machine that well, the tape is initially considered to have an unbounded length, that is. So bounding will be fixed. Only finite contiguous portion of tape, only contiguous portion, that is a joint it is a consequences, the sequence that is in the sequence that contiguous, that physically the memory adjacent, the adjacent memory, that is a finite contiguous portion of the tape whose length is linear function. So that is a contiguous portion. And what is the length? So that length will be determined or decided by the linear function. So we have seen in the previous slide. So that is a C into input length, or K into input length, that is a Kn or Cn, right? Cn we have seen. either C or K, both are terminal, most of the others they are using. So that linear function will be SS. So that is a maximum bound. So the number of cells going to be less than or equal to this linear function. So that we have discussed, that initial can be assessed by the read rate head. So hence the name linear bounded automation is evolved, as emerged, or coming into popular in the literature contribution. So it heaped into the contribution of the literature. So linearity there to decide the length of that tape, that bounding will be fixed. So this limitation make an LBA, that linear bound automata, a somewhat more accurate model of a real world computer. So it is a more accurate model compared to the real world computer than Turing machine. So Turing machine was almost is a kind of analogous, the use infinite, the magnanimously increase for the very complex problems. So where we can strip down into discrete way with further with the linear bound automata, which model of a real world the PC accurate, more accuracy will going to be yield, whose definition assumes unlimited tape, right? As we observed in the Turing machine, unlimited. The strong and weaker definition, the governing to same computational abilities, the governing to the same computational ability of the respective automation classes. So the both side strong and weaker definitions going to be computational ability to assess especially this automation classes. So due to the linear speed up theorem, so linear speed up theorem will be marginalized, normalized the further definition for this the linear bound automation. So that is a strong and weaker definitions lead to, or leading or pleading to the same computational abilities of the respective automation. So from this we have discussed about operation, about the concepts we have related to this what is called linear bound automata. So we can see the we have seen in the previous that context sensitive languages and undecidability and linear bound data relations, right? So now you can see that how close with this CSL, the set of strings accepted by the non-deterministic LBA is the set of strings generated by the CSC. So that any strings which is accepted by the non-deterministic LBA is also a set of string generated by the context sensitive grammars, here excluding the null strings. If it is include the null string, what will happen? It become undecidable, right? So that LBA become undecidable. So because a lot of curse for this Turing machine automata, so that will go to be discussed in the further. So that is sometimes the machine going to be in the infinite loop, it will be hang, so it will be in the non-terminating situation. So in that case it become the complex. So that will is a separate discussion. Further the if you include the null string, it become undecidable. So that's why, so to avoid that, so solvable, we want to solvable, so that going to be yield decidable results. So here excluding the null strings, we are safe that LBA is a very competitive and it is a healthy discussion, or it going to be yield some results. Now we can give important results if L is a CSL, then L is accepted by the linear bound automata. So if L is a context sensitive language, then L is accepted by LB automation. So the converse is also true. So LB, the linear bound automata accept the language L and is also going to be accepted by the context sensitive language. Vice versa true, right? So the construction and the proof of the similar to those for Turing machine with some modification. So the proof also there for Turing machine with a little modifications going to be observed that. So there are acceptors for the class of context sensitive languages. So there are acceptors for a class of context sensitive languages. So here we can see that the only restriction imposed on a grammars for such language, that no production maps a string to a shorter stitch. The no production maps to a string to shorter stitch. So strings should be equal or more, should not be shorter. So that restriction is imposed here. The rest restriction is exercised here. So thus no derivation of string, there is no derivation of strings in a context sensitive language can contain a sentinel form longer than the string itself, right? So sentinel see that the barcode or some remarks, that is, so sentinel, that initial one form a longer than the string itself. That is, since there is a one-to-one correspondence between the LBA and such grammars, so there is a one-to-one correspondence, so one-to-one mapping, right? So that the mapping from one to one, so that will be happen, that is, so LBA is going to be a match with the sub grammar, such grammars, so that correspondence will be going to be established. So no more tape than the occupied by the original string. No more tape than the occupied by the original string is necessary for the string to be recognized by the automation. So no extra tape than the occupied by the original string is necessary to be recognized by the automation. So further we have discussed in the previous session also, to add on to that, so context sensitive language related to this context linear bound automata, so that sensitivity of production of any product satisfy that, or the length of this what is pound symbol, the length of the pound, that is a string. So length of the string is going to be major factor. Sensitive grammar, any generative grammar G is equal to a dash of P, the production in P context sensitive, so no empty productions. So we have seen that, so that become what we have seen in the previous, so that become what we call that is the undecidable. Context sensitive language sensitive if there is exist context sensitive grammar, that is G, such that either L is equal to L of G, or L is equal to L of G belongs to also belongs to that empty. So empty is there also, but alone empty not allowed. Along with this language, empty is allowed. So we have that context sensitive language privileges. So from this concept, so we have discussed in length the concept of the linear bound automata theory with help of the various that challenges and operations and the limitations we observed. Further, that is a context sensitive equivalence of context sensitive grammar to the LBA. The language is accepted by the LBA if and only if it is generated by the sensitive grammar, right? We have seen that. So that is accepted by this LBA. It is certainly, definitely, it should accepted by the CSG. Just like a equivalence between this context free grammar and push down automata. Context free grammar and push down automata. So given an X in CSG G, input X in the context sensitive grammar G, it can intuitively see that and LBA can commence with a S, string S, and non-deterministically choose all derivations from the S. S is the start of the production. See if they are equal to input string X. See if they are equal to input string X. So that is going to be observed here, because the context sensitive languages are non-contracting. Context sensitive languages are non-contracting. The LVA only needs to generate derivation of length, going to be length that is found. So that is a length of the x. So generate the derivation of length. So how many depth, what is the depth of the derivation? So the go on to be go in a deeper way. So that is restricted to length of the, that is a string, there is a length of the x. So this is since it generates the derivation longer than x, so it's going to be generate the longer than the x. It will never be able to shrink to the size of the x. It is longer than the x. It is not lesser than the x. That is a limit in that. It obviously the generates the derivation. It is longer than the modulus of the x. That is a total length, the positive value. So longer than the length of the x, it will never stop to, never going to be diminished or reduced into the less than the x. So that is the equivalence going to be established the between the context sensitive grammar and linear bounded automata. So from this, we have discussed the enough concept about linear bounded automata origination. So how it evolved, and how it was the converted the added some attribute to Turing machine, and we call it a linear bound automata. So that infinite length will restrict to finite, and two tapes are there, one for input and other for working tape. And also we have observed the challenges by this the deterministic space and non-deterministic space. Two challenges were there, those problems are solved. Still the open problem is there, that non-deterministic space is not equal to deterministic space of the Turing machine. So on behalf of the linear bound automata, so operations also we have seen, the model also we have seen, and the relation between this what we call context sensitive language, undecidability, and linear bound automata, which are inherited from the Turing machine philosophy. So that we have seen in length. So this material or further information is definitely available in the following books. We have referred that books, that is Ilan Rich, Automation, Computability and Complexity, Postdates and Pearson Education. And the most important book is called Misra and Chandrasekharan, so third edition, Theory of Computer, that is a Prentice Hall of India. Apart from the additional information, we can borrow from the reference book that John, that is a Hopcroft, Motwani, and Ullman, that introduces computer theory, automata theory, languages and computation, third edition, Pearson Education. Michael Sipser also provided some information, that is Engage, so introduction to the theory of computation. So also the one more book called Introduction to the Language and Theory of the Computation by my John C. Martin, that third edition, Tata McGraw. Apart from this, there is also some internet, also some magazines also available. So I hope it is clear from the concept the linear bound automata. Thank you for patient listening of the topic linear bound automata. Thanks for the coordinator and moderator providing the environment ambience to produce this video lecture. Thank you once again.